12 of us. I like it. We're a sturdy little group. We have to send out a search party at some point. Maybe this Thursday I'll see more people. That would be amazing. I have not been the best at getting on people about not coming to class, and I'm not used to doing that because this is freaking college. So you pay money and you come or you don't come. It's kind of crazy, but I need to get on these people, get them to come to class. So I appreciate you being here, or at least, logging in and then going back to bed. I'll never know, but at least you're turning the computer on. That's good. That's a huge thing. I got one question in chat, section 6.5, number 24. Let's take a look at that. Oh, all right. This is written a little bit funkadelic. Let's see. So if I rewrite this a little bit, like, let me ask you this question. What would I do with number 22?
Rewrite.
Say what?
You first rewrite it.
True.
Like log x squared.
Yeah, so I'm going to use the property because I want to be able to use the property a log plus a log with the same base. I can rewrite that as a product inside, right? Is everybody with me? I want to be able to do that, but I don't have any property about 2 logs added to 3 logs. There's no property about that. I need 1 log plus another log, right? So if I get that 2 out of the way and I get that 3 out of the way, now I've got log x squared plus log x plus 1 cubed. And now I can do it. Now I got log base 10 of something and log base 10 of something. Right. And now I can do the property that says if I have the log of something plus the log of something else, I can write that as the log of the product. Okay, is everybody cool with what I've just done? Anybody not cool with what just happened? Okay, all right. Go ahead, chat. Hold on. I'm not sure. All right, I'm not sure which question you're answering, but I'll take that as you're cool. You're okay with it. So 24 is written a little strange. So let me rewrite. So the first part of 24, what would I do with the first piece of 24, the first log? Uh-oh, is my screen share flickering? No? All right.
Yeah, not for me.
Like, you could direct that towards me, but I felt a little weird, like, oh, he's not asking me. Okay. So like the first piece of this would be log base 7, bring the 4 back up. Now, what's making the rest of this weird is they're not written as coefficients. How could I rewrite this with a coefficient? What would the coefficient be?
1/3.
Yeah, 1/3. So now they're just powers that you can bring back up, bring up. Okay, that's all I'll do. I'll let you guys finish that. Is that okay? Was it an issue about how they wrote it? Okay, good. And again, whenever I ask if it's okay, your answer can be no. I'm always worried that somebody's like, I don't have a flipping clue what you just did, but I feel like I should say yes. Don't do that. Say, I don't understand what the hell you just did, Joe. Maybe show a little more respect. I don't know, but it's up to you. Anybody else? Any other questions? Homework's going great.
In the next section, or in the next chapter, 6.6, there's a whole section where you're using like bases and logarithms to solve.
Yeah.
And I think I got all of them incorrect, and I'm just missing some step, or I'm doing it in the wrong order.
Oh, shit. Well, let's take one problem. Let's see. So something like, well, let's see, blah, blah, blah. Here. No, maybe. Well, this is kind of dumb. All right. Here, this whole section.
Yeah. All right.
right? Yeah, most of these are stupid. Oh my goodness. How long has it been since I looked at this? Why is this book doing this shit? Yeah, oh well. We do what we can with what we got. Oh my goodness. All right. Yeah, these are really silly. These problems here are kind of silly. Every single one of these, well, let's see, except for like 38 maybe. So can you give me a problem? Which problem? Give me one problem that gave you trouble that you got wrong.
I think it was 15 as well. But that one was different.
All right. So, okay. So were you able to do, oh, scheisse, number 11 or 12? Was that one that I assigned? I can't remember the homework for this.
Yes, it was every third one. So like 12 and 15 both.
So 12 one, okay?
I think so.
Okay. So what you had to do with number 12 was divide by 2 so that you can attack both sides with natural log. So the first thing you want to do, all right, guys, something general for any equation is you want to isolate the thing that has your variable in it, because then you can attack that thing, right? So here I would divide by 2 first, because then I can attack the e that's got my x like hostage inside. So I'm going to attack it with a natural log, right? A wild e to the 6x appears, and I attack it with a natural log. So number 15, there's just a little more shit to do. What am I trying to get by itself? Where's my variable? What term has my variable stuck in it?
The 10p.
This thing. So I'm going to add 7. I'm going to divide by -8. Right? I'm going to try to get that piece by itself, because then I can attack it with the appropriate log. Does that make sense? So I'm going to, if I add 7 to both sides, I get -17. And then if I divide by -8, I get something admittedly not beautiful, poor little thing. But then I can just do what to both sides? What can I do to both sides, guys? Let me rewrite this a little bit better.
You can log it.
Holy crap. Yeah. Hold up, guys. Oh, shit. Sorry. Oh, why am I doing it? I should be doing this up on the board because it's driving me crazy. Okay, so yeah, I can do log of both sides, which really kicks ass because these just die. Right? So I get p plus 7 equals whatever this number is, and then I can just subtract 7. Okay, so I did a homework problem for you. Damn it. I didn't mean to. Do you guys see?
Yeah, I just got mixed up in the order of which to do things a little bit.
And real quick, I have to do this. So if I had a problem that looked like this, what's my first order of business?
Moving to 5.
Yeah, I want to isolate the thing that has my variable stuck in it. I'm not going to square right now. That would so desperately, you want to FOIL this shit? No, let me back up. Let me get my radical by itself so I can attack it. Let me get my 10 to the power thing, because that's where my variable is, so I can attack. Let me get that by itself so I can attack it. I like it. I like to pretend like I'm teaching how to be a tyrant of a country. You're like, I don't like this element. We'll isolate it, sir, and then we can bomb the shit out of it. So this is not a good life lesson. Unfortunately, we are one of the countries.
I mean, unless we're planning on becoming dictators, then it's great.
This is, well, I don't know. Maybe I'm going to make somebody go, that sounds fun, dude. Oh, shit. Okay. Oh shit, I got a lot of chat going on. Hold on. Natural log. Those were wrong answers. Wait, I don't understand what you did with the -8 and the +8. Oh, okay. There's no +8. Hold on. Let me back up a second. All right. Well, let me just clear everything. It's better just start over. All right. So all I did was I added 7, right? So I know I want to isolate where my I want to get this by itself. So I'm going to first add 7. Is that cool? Now, why is this not by itself yet?
Because it's being multiplied by -8.
Yeah, so how do I kill something that's being multiplied? I divide by it, right? Now stay with me. So there was no +8 doing shit. But those cancel, and those cancel, and those cancel. Right? Everybody with me? That's all. Okay. So that's where you get this, and then you can take a log of both sides, and blah, 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 blah. Okay. So isolate where your variable is. So then you can attack that directly. That's like a general rule for any equation. All right, I like it. Why is that a good thing to talk about right now? Because you're going to get a whole bunch of different kind of equations on the midterm. Woohoo! Okay. Everybody see that the midterm solutions video is up? Did I already say that? No, because I just did it yesterday. No, all right. It's up. It's up if you want to look at it. But boy, did I just say practice midterm? I don't know if I said midterm. You're like, oh, great. The guy put the solutions up for the midterm. That kicks ass. No, the practice midterm. Okay. Anything else from homework while I'm looking at it? Did I miss anybody's question?
That sums up the chapter I was having the most problems with recently.
Okay. Cool. So everybody else is good? All the homework is fantastic. No problems here, Jeff. Nothing to see. Okay. I want to believe you. All right, let me see. And that's not saying I don't have faith in you. That's saying that there are some funky ass problems. And if I don't get questions about them, I get worried that nobody's doing them. All right. So what I want to do, if there's no other questions, let me get a kind of a game plan for the week. Today we're going to probably finish 7.2, maybe look ahead to 7.3 a little bit. Tomorrow, I might start off with a little bit about chapter 7, but then the rest of the class will be devoted to review for the midterm, right? So we have time tomorrow to ask questions from anything that's related to the midterm. Chapter 7 will not be on the midterm. Yes? Because you haven't had time to do the homework. Okay. So we have established what radians are, for sure. Let me turn off my dragon. How to turn off your dragon. Well, this is how you do it. All right. So what's the main thing to know about radians and degrees? What's the main connection between them? Can anybody tell me very succinctly? Like using some numbers even? What's the connection between radians and degrees?
Degrees aren't real, but 180 of them make a radian.
I like it. So 180 of these made up little chunks of a piece of pie, right, make up pi radians. I like it. Which is really neat. Now think about what that really means. I mean, just take a second and really think about what this means. What is a radian? Let's see if anybody, what's a radian tell you? Yeah, sure. What's the number of radians in a degree? What's it tell you? Why is it called a radian?
It's based on the radius.
Based on the radius. I like it. All right. So it's the number of radii. Well, where's all my pens at? Damn. So pi radians. Pi is approximately 3.141596. That's as far as I know. That means that however big this circle is, however small the circle is, however big the circle is, exactly that many radii fit here. I really want you to think about that. So if you take a little bit more than 3 radii and bend them, they would fit on the circle. Why does it work no matter how big it is? Because if it's a smaller circle, the radius gets smaller, so it's still the same proportion. Okay, maybe. That's why I can use this very physical idea of a radian instead of stupid little degrees that somebody made up, right? They're like little degree fairies that our grandma saw in the back garden when she was a little girl. Like, I don't know, Grandma, I'm going to use the radians. I love you, but I don't know about them fairies. All right. That took a really weird turn. I'm sorry. My brain is somewhere else. I don't know.
And I guess if it didn't work, it wouldn't really be a circle, huh?
Yeah, exactly. I like it. All right. Now, the thing that I tried to shove into the end of class last time, we're gonna build our way back up to that. Okay. But there are a couple things that I kind of neglected to go over that's left over from section 7.1. So we're going to go over a couple things left over from 7.1. Then we're going to get back into looking at right angle kind of trigonometry stuff, right? And then we'll see how much time we have left. Okay, might as well get off my ass. All right. So the things that I left over that I didn't talk about from 7.1 are related to linear velocity versus angular velocity. So, for example, for some reason, I watch a few too many, like, do you realize there's a lot of flat earth people out there right now? If you are a flat earther, don't tell me, because at least you're in college, so maybe you have a chance to not be a flat earther anymore, but just don't tell me, because I can't handle that. So there are a lot of flat earthers still out there, believe it or not. Yes, way to go, world. All right.
I've met
There are
one.
flat earthers all over the globe. Sorry?
I've met one person.
Huh? You met one person, one flat earther?
Yeah,
And-
told me. Yeah,
Say again?
there's one person I met.
Yes?
He told me the earth is flat.
Oh my God, I'm sorry. Yeah, all right. Oh man, okay, all right. So let's get past that for a minute. So what does that have to do with anything? Have you heard that if you're at the equator, you're going like 1,000 miles an hour or something? Has anybody ever heard that? Which is insane, because it might technically be right. It's sort of like if I'm on a merry-go-round, right? I'm trying to remember what they look like. They have, remember merry-go-rounds? And not merry-go-round, but what do you call the little things, the spinny dudes? It's not a merry-go-round, but you hold on for dear life. And
Carousel or
I can't remember.
oh, the thing at the park.
Yes, exactly. Now, imagine standing here and imagine that this takes 1 day to rotate all the way around. All right. Now imagine making this really, really big. It would and still letting it take 1 day to rotate. That's nothing, right? Do you agree with me? That is nothing. If you translate it to linear velocity, you get these crazy numbers, and they're like, see that shit? I don't feel that. Oh, all right, flat earther. All right, sorry. I might be making somebody feel uncomfortable, and I don't care. You should feel uncomfortable. All right. Sorry. So the connection between linear velocity and angular velocity is a very interesting thing to study. So what do we have? We have, let's talk about linear velocity. Holy crap. And actually, let's use the more, we'll say speed, because velocity is speed plus direction. So let's not go there. Let's talk about linear speed. We're still going to use the letter V for it, but oh well. So we're sort of, instead of using D for distance, I'm going to use S. Remember, that's the arc length. But I can use S for displacement. So S is kind of like a general letter for displacement. Let me turn off my little UFO light over there. Okay. Now stay with me. This is kind of neat to try to connect this. So angular speed. Angular speed. So the V is the letter we've picked for velocity, for linear velocity. It's distance divided by time, but instead of D, I'm going to use S for arc length, S for displacement. Stay with me now. So linear velocity is in what kind of units? Give me an example of the units for linear velocity. You're in your car. How fast you going?
Miles per hour.
Miles per hour. So you got miles per hour. You got meters per second. You got linear distance per time. So it's the rate of change of distance per time. So what do you think angular speed should be? The rate of change of what per time?
Radian?
No.
But
Sort of,
the
yes,
angle?
sort of. Yeah, so angle. So the rate of change. So if I'm moving in a circle, the angular speed will be how quickly my angle is changing over time. So the Earth rotates at 15 degrees per hour. Right? And why does that make sense? Let me see. I'm pretty sure I got that right. 15 degrees per hour, because 15 degrees times 24 hours
It's 360 degrees.
360. There you go. Right? So its angular speed would be 15 degrees per hour. Right? That would be the Earth's angular speed. Is everybody with? And that's at the equator. Let's just be careful. So angular speed, we use the symbol. This is not a W. This is actually an omega. An omega is like a W that got all fancy. So it's not a W, it's an omega. The angular speed is going to be angle, the rate of change of the angle per time. Okay, so it's very, very similar, and that kind of makes sense. This measures how far you've gone linearly, whereas this measures how far you've gone angularly. I like it. Just making up words. That's how English works, kids.
Is angular the circle?
What is this circle meeting in? Anybody remember? What's this? I'm not an alpha male or a beta male. Anybody remember what this is?
Theta.
Theta. I like it. That's theta, and that is the most generally accepted variable that represents angles. Radians or degrees, whatever you're talking about. Sort of like, what's the most generally recognized variable for numbers in algebra?
X.
X, thank you. So is X the only variable we use? No, there's other ones. Just the same way as theta is not the only one used for angles, but it's like the most commonly used one. It's the base one to use. All right, so everybody with me so far? Nothing major. Linear velocity. And here's what angular velocity, because it's all about measuring how much the angle changes over time. So I'm here, and then how much of an angle did I go through over time? Okay. So what's the connection between these two? Well, somebody remind me, what's the formula? So if I'm moving in a circle, right? How far have I gone how far have I actually traveled? What is this little piece of the circle? Right, so how do I define, if I have an angle, what is this thing called? What is that length called?
S.
S, I love it. S, arc length. Arc length is S. And do you guys remember what the formula is for it?
R times
It was
theta.
very similar to a triangle.
R.
Well, careful, that's area. This is just length, so it's R times theta.
Oh, okay.
All right, let me stop for a minute. I love you guys. I want you to notice something that's going to become, we're going to get there. It's going to be neat. Do you see how do I change something from angular to linear? So this is how the degrees I go through or the radians I go through, while this is the actual distance I travel. So what's the connection? I multiply by r to go from angular distance to linear distance. Linear in this case doesn't mean straight line, by the way. Linear just means you follow a path. It could be curved. I know that's weird, but just go with me. All right. So the connection between this and this is that. So if I take this equation, let me see, hold on. Do I want to, how much room do I need? I guess not too much. Let me start with this one. Yeah, let's do it this way. What is theta from this equation?
S over R.
Oh, no, from this equation. Just multiply the t up, right? Yes, okay. So that means that this can be written as r omega t. Make your little W curvy. All right. So now I can take this equation. So now I've got the linear, I've got this distance I travel. If I'm going at this angular velocity, I'll travel this distance. So that's how I do it. So if I go 15 degrees per hour for so much time with the radius of the Earth, it'll tell me how far I've actually traveled in space, right? Okay, maybe as I'm rotating on the surface of the Earth, right? Okay, let me stop for a minute. And now I just take, now I can make the connection between linear velocity and angular velocity, because if I take my linear velocity down here and I replace s with this, look what happens. Shabow! So watch, I love this connection, and they did not make this connection for me. And I always can feel some of you guys sort of like, I have turned off now, Jeff. I'm not paying any attention, but this formula, this formula hopefully makes sense. It's kind of the same, it's analogous to this formula, just with angles. We know this formula from before. Put them all together. I get this connection between linear velocity and angular velocity. Look at what's beautiful about this. How do I go from angle to distance multiplied by r? How do I go from angular speed to speed over distance to linear velocity? I multiply by r. I love that. That's the connection between the two things. Okay. I could have done, I don't know why I chose to go that way. Let me show you, well, real quick. I could have gone this way. Velocity equals r theta over t. And what was theta over t? That was omega. Well, that would have been quicker, Jeff. Oh, well, too bad. So there's a lot of different ways to connect velocity, linear velocity, and angular velocity. I like it. So we got this bad boy now. Okay. I like it. So let me ask you this. Let me give you an example problem. Let's see the different ways they can give me these measurements. So let me put up here, S equals R theta, V equals R omega, omega equals theta over T. Okay, that's good. Let's say I have, I'm riding my bike and my tire, let's say it's got a 14-inch wheel on it, right? 14-inch, should it be diameter? I don't know. Is that a big ass wheel?
That's a little big, but it's not unreal.
All right, we'll stick with that. I'm on this big ass bike. I'm on like a bike from the old days. Remember those bikes where they had like this? They had a seat over. I can't remember. All right. So stay with me now. And let's say that I am moving at a velocity of, how do I say this? So this is 14 inches. And let's say I'm just kind of moving at a velocity of 7 inches per second. I have no idea. Okay. So that's my forward movement. I'm going 17 inches per second. So how am I gonna, so I want to know what's the angular velocity. So does anyone see a quick way to get that? What do I know? I know V. What is this?
The R.
That's R. So what's the connection? How do I figure out the angular velocity?
Divide by 14.
Yeah, because the formula is R omega is V. So if I do 7 inches per second equals 14 inches times omega, divide by 14, right? Now watch what happens. I've left the units in here on purpose. So if I divide by 14 inches, I get the inches cancel, correct? Right? The inches cancels. They have to. They do. Bam, bam, they're gone. 7 divided by 14 is a half. So omega is 1/2 radian per second. Or you can write it as 1 radian per 2 seconds, whatever way you want to write it. Remember how the radians kind of come in and go out as they are needed. So that's a relatively easy problem because I just had to use this one equation. All right. Now, watch this. All right, I'm going to erase this. You ready? What if I said, all right, let's say I've got a wheel. It's rotating. That's interesting, Jeff. Rotating at 4 rotations per minute. And I want to know what's the angular velocity in radians per minute. Not as hard as you would think. You can do this. So if I have any wheel, do you see how I didn't even tell you what the radius of the wheel is? So some of you guys might be going, how the shit can I do this, Jeff? You gave me like nothing. Can somebody please tell me? I don't care how big or small the wheel is, however big or small the wheel is, what is one rotation? No matter how big or small the wheel is, what is one rotation? How many radians?
2 pi R.
2 pi. Careful, no R. Okay. Sorry. I don't mean it to sound like that. Right? Stay with me now. So 2 pi radians. So 4 rotations would be how many radians?
8 pi.
8 pi rads per minute. Done. So they're going to have some problems where they talk about rotations. You guys semi with me? They talk about rotations. All a rotation is, one rotation is 2 pi radians. Right? Don't treat that like it's some special, oh, no, it's bullshit. Of course, one rotation is 2 pi radians. We know that. It's nothing special. It's just that when you see this word, you're like, what the shit does that mean? Just rotate it once. It's 2 pi, so 4 times is 8 pi. Done. I like it. So now, if I tell you, let's see. The radius of this wheel is 3 feet. What is the linear speed? Ooh, yeah, can I do that? Yeah, sure. What is this, by the way? What symbol should I put here? What's the variable I put here?
Omega.
Omega. And what's the formula for linear speed that relates to omega?
Is it the V equals R omega?
Yeah, okay. So nothing crazy happening. Right? So then the linear speed would be R, where'd I put it? 3 feet times omega, 8 pi per minute. So it's 3 feet times 8 pi per minute. So it's going to come out in feet per minute. So then, you know, whatever the hell that is. This time you want to, you really kind of should write this as approximately whatever the hell 8 times pi is, right? What is that? 25.12, roughly. 1, 2. I don't know. Nobody's going to help me. You're just going to watch me stare at my ceiling and think. I think that's about 25.12. And then if you do 3 times 8 pi divided by, 3 times 8 pi, to figure out about how fast that is, right? Because you're not going to say to somebody, hey, I was going about 8 pi feet per second on my, what the hell are you talking about? Right?
Yeah. I got 25.13 when I just
Over
did
there?
that.
Oh, man.
Yeah.
All right, I got to retire tomorrow, kids. That's done. I'm over. I have been canceled. All right. Sorry. I don't mean to perpetuate that dumb cancel culture, whatever. And then who's got what down here? 3 times 8 pi. That'll be 75.4 roughly.
Yeah, 75.4.
All right, now somebody's got a question. And what's the units on this real quick before I get to that question?
Feet per minute.
Yep, feet per minute. So make sure if you're talking about a velocity, it's got to be something with a ratio of units, of course, because a velocity is a rate of change over some time. I thought linear speed was, oh, okay. So remember, these are the 3 equations that kind of relate angles to everything. Linear speed itself is distance divided by time, and I'm just using the letter S for distance instead of D, right? Remember D equals RT? Distance equals rate times time. So then isn't the velocity equal distance divided by time? So now I'm using V instead of R for rate. I'm using S instead of D for distance. It's the same formula, right? Nothing major there. But this is an old formula. This is not really for angle stuff. What's the other question? Omega by itself. Oh, I did put that up there. There's omega. Right? That's omega. Omega is angular velocity. So it's the change in the degrees or the change in the angle per time. Somebody's asked me questions in the chat, sorry. Does that make sense out there? So I know we proved earlier that this is definitely true. V equals R omega. And I love that analogy. Linear stuff equals R times angular stuff. I love that. That kicks so much ass. Does it continue into acceleration, Jeff? Yes, it does. In a weird kind of way. Oh, I see. Okay. I'm sorry. Don't worry. The main important thing between speed and velocity, those words don't necessarily matter, especially in everyday English. What's important here is angular blank versus linear blank. If you want to call it speed, if you want to call it velocity, it doesn't really matter. Okay. Is that better? So what's important is the angular blank versus linear blank. That's what's important. Doesn't matter if you call it speed or velocity. It really does, but not in everyday parlance. Hey, look at that. I don't use that word too often. All right. So that's that. There's going to be several problems with rotating flywheels and gears and shit. Yeah. And they like, what do you call it? When they're in the water? Paddle wheels, not paddle wheels. I don't remember. Okay. Okay, so that closes the door on section 7.1. My neighbors are doing weird things outside. All right, now I want to, I don't like, all right, I don't like the standard way this trig stuff is taught. I really want it to make sense from the beginning, and I try to lay the groundwork. I of course try to do too much in too little time. Watch this. Let me do an equilateral triangle. So can somebody tell me in an equilateral triangle? First off, what does that mean? Equilateral.
All angles are the same.
True, but definitely by the word itself means all the sides are the same, which means all the mouths have to open the same amount, right? I know I'm weird. I look at these as mouths, but they all have to open the same amount since the sticks in them are the same size. So I'm just going to call this distance x. And these are all 60 degrees. Is everybody cool with that? Why are those all 60?
Because they have to make 180.
Have to make 180. If they're all the same, divide by 3. Bam. All right, let me stop for a minute. Can I use Pythagorean theorem on this thing? What's the only kind of triangle that Pythagorean theorem works for directly? Because later this semester, we're going to learn how to make, listen kids, listen, little teaser, you ready? You're right, it's a right triangle. Later this semester, we're going to learn another term to put on Pythagorean theorem so it works for every triangle. Isn't that neat? Isn't that cool? So you guys are like, I don't know yet. We'll find out. Okay, sorry. I didn't mean to get all up in your business. All right. So this Pythagorean theorem, as we know it, won't apply here, but I can make a right triangle by just chopping this straight down the middle, which makes this angle here what?
13.
Oh, 30. Okay, you were, I think you said 13. And then this, of course, becomes a right angle by definition, straight down. So it's a right angle by definition. All right, let me stop for a minute. Is everybody cool with what just happened? So let me draw this right triangle here. I'm going to need some help. I know that's x. I know this is 60. I know this is 30. I know that's 90. So now Pythagorean theorem will work, but what is this?
1/2 x.
Good. And this we'll just have to call h. Okay. Now, here's the neat thing. So now this is sort of like where we left off last night. I know I tried to throw everything in at the end. What's interesting is no matter how big these sides are, can you guys hear that outside? Yeah, I'm sorry. All right. All right. I don't know what's happening. So no matter how big these sides are, the ratio of these. So let's see. What if we said, what's the, let me give these things some names. This is unfortunate that I picked the letter X, but can you guys see why I would call this side the X side?
Yes.
I would call this side the Y side.
Yeah.
Right. I'm going to call this one. Oh, this is really unfortunate. Man, Jeff, you have picked some horrible. And this, of course, would be the hypotenuse. All right. Hopefully I spelled that right. It looks like too many U's. Yeah, there's way too many U's right there. Oh, we'll do it. All right. Now watch. So what would the ratio of the X side to the hypotenuse be? Ratio of the X side to the hypotenuse. So if you do the X side divided by the hypotenuse, what do you get?
To that.
No, what's that? So you take the X side divided by the hypotenuse, right? What's that?
Uh-huh.
Yeah, x halves divided by x is 1/2. I love you guys, because you can do x halves times 1 over x. Bam, you get 1/2. Now listen. I really, has everybody followed? I started with a generic, could be any equilateral triangle that has ever existed or ever will exist is right here, correct? Because how big are the sides? Any size you want. How about complex numbers? I don't know. Maybe not that, right? But maybe so. I don't know. We're not going to talk about it. I then constructed a right triangle out of it. No problem. And then, of course, you guys, everybody agrees that I cut that bad boy in half, right? So that's why that's this. So this, notice something. For a 60-degree angle in a right triangle, the ratio of this side to that side will be 1/2 no matter what. Does everybody understand? I don't care how big or how small. If you got a little tiny triangle with a 60-degree angle right there, the ratio that side to that is 1/2. You got this big ass, I can't even draw the whole thing. Whoa, man. The ratio of the x side to the hypotenuse is 1/2. So on one level, that should not be surprising, because if I make this twice as big, all the sides get twice as big. So of course the sides divide to be the same number. So on one level, all of trigonometry should be, well, duh. And I don't say that to be mean. If you're like, I don't understand what the hell's going on. I want you to realize if I blew a triangle up, since all the sides would grow by the same amount, when you divide any two, they'll always be the same number. That's really all trigonometry is building off of. So obviously, I want to say this is a function. I want to come up with some function for this. And when I evaluate it at 60 degrees, the answer is 1/2. So I know one input and output for this function that we don't even have a name for yet, correct? Okay, I like it. There's a few more triangles you could do this with. I did a triangle yesterday, an equilateral isosceles triangle, 45, 45, 90. I did that one yesterday, but let's do this. So this is one idea, right? And of course I can build all these other ratios, and that's what I want to focus on now. So I'm just trying to lay the groundwork that there should be some kind of functions I can create that relates to every ratio you can make between all this stuff, all the sides. Each one gets its own function, because for an input, it will always have the same output. So that sounds like a function to me. Woo-hoo. All right, so that's one idea. That's why the trig functions should exist. If they are the things that are the ratios of these sides, they should exist. There should be a function because there's a connection, there's a relationship. Now, let's talk about what we choose these to be. So let me give us a general right angle. Now, we're going to make the connection back to the unit circle after we kind of lay the groundwork of each function. And the neat thing is, just remember that when I have a unit circle, it is made up of triangles, because right there, I've made a right triangle. So everything we're discussing right now is also going to work in the unit circle because it's made up of a bunch of triangles. Which is the last thing you expect to say to somebody. That circle is made up of a bunch of triangles, but you understand what I mean. It's right there. Okay, now, so I'm going to call this the y side, the x side. I'm going to call this, let's call this, well, all right, let's stick with h for now, for hypotenuse. And we're going to give this guy the name theta. We'll go ahead and name this guy. What do you guys want to name him? Who wants to give this angle a name?
Alpha?
Alpha, I love it. Kick ass. Little alpha. Okay, now. One ratio that we want to work with is the one that I just put down earlier, is the x side to the hypotenuse. So we want to work with this ratio, and we want to give that ratio a function name. the input for this function should be the angle, because if I make the angle grow bigger, then one of these two is going to change. So that's why there's a single output for a given input. Let me shut up for a minute. I really want that connection, because that's the connection I think I was missing for a long time right after I learned pre-calculus. I understood some of this shit well enough, but I wish somebody would have made that connection for me. Why does it make sense these functions exist? These trig functions exist. It's because for certain angles, these ratios will be certain defined numbers. So there's a connection, there's a relationship that I can define a function on top of. That's why. Okay, all right, that's the last I'll say that, I'm sorry. So what we call this ratio, we call that the cosine of the angle. So that's written more better. Is that what you're about to say, Jeff? Yes. Cosine of theta is equal to the x side divided by the hypotenuse. Now, I want you to let me make a big deal out of this right now, because this is the best way to learn this shit. Automatically, that's my opinion when I say it, but it is the best way. Some of you guys might have heard of something called SOHCAHTOA before. Has anyone ever heard of SOHCAHTOA? Does that sound familiar?
Once or twice.
All right. SOHCAHTOA is bullshit. All right. Some of you guys might have just made some enemies, unless you're, I might have made enemies like from day one. But if you know SOHCAHTOA, I'm sorry. I apologize to you. It's bullshit. And I don't know if you have been with me long enough to trust me. So much makes so much more sense if you understand cosine likes x. Cosine goes with the x side. Cosine is all about x. Cosine likes x. Okay, I think I've put that in there. Now listen. So let's make this deal right now. What about alpha? So the reason this is the x side is because theta is the base, right? So this is drawn in standard form. So can anybody see for alpha, you'd have to look at it like this. Do you guys see what I'm saying? I really want you guys to be with me. This is in the base. That's why that's x, that's y, right? And that's the hypotenuse no matter what, because it's across from the 90-degree angle. Everybody with me? Alpha's not in the base. Would you say, do you guys agree with me? Alpha is not the base angle. Does that make sense? Everybody? Yeah. If it was the base angle, wouldn't I have to turn this around?
Yeah.
Or equivalently, I could just do this, right? In which case, this would be the x piece because it's running left and right. And this would be the y piece because it's running up and down. Do you guys? So as long as your angle is in the base, this works. Okay, maybe. Okay.
What happened when you switch a theta and alpha? So
let me make the point right now. So cosine of alpha, and again, this kind of sucks with the letters I've got, but so what? Alpha, what would be running left and right would be y over that hypotenuse. Yeah. All right. Well, let's not go there yet. Well, I'll do that when I don't have x and y up here. So right now, we got to know what the base idea is for each trig function. Just stay with me. We're going to do an example like that when I get some numbers up here. What about this ratio, y to h? Now, this is interesting. There's got to be a connection between these two functions because what we do is we call this one the sine of theta. Sine, and this one is cosine. Interesting. Right? So this kind of inherently tells you there's a connection between sine and cosine. And there is. Okay.
I have a quick question.
Yes.
Does theta have to be a smaller angle?
No,
than
definitely not.
alpha?
Nope, not at all. Right? I didn't set that up. So theta can be as big as it wants to be, as small as it wants to be, as long as this is 90. I like it. And alpha could be as big or small as it wants to be, as long as that's 90. I like it. So the way you write this is sine theta. All right. And then really there's 6 total trig functions, but 3 of them are a little bit silly because they're the reciprocal functions there. So there's going to be a function that is h over x, and there's going to be a function that's h over y, right? So there's a third primary trig function, and that's the last ratio we have to make. What's the only ratio we haven't made yet, really?
Y and x.
Yeah, y and x. I love it. So let me consolidate some of this stuff. All right, you guys ready? I'm going to rewrite this stuff up here. Hold on. So we got sine theta is y to h, cosine theta is x to h. And now I've got tangent of theta is y to x. Have you guys ever heard tangent line? You certainly heard of somebody going off on a tangent, right? I like it. So sort of like, here's the conversation, and this person goes like this. So that actually is the mathematical idea of a tangent line. It's a line that sort of is the same as the slope at that point for the original function. Holy shit, that was a lot. Sorry. It's sort of like if I was swinging something in a circle, the tangent line would be where that would fly if I cut the rope. It's kind of like the direction it's going at that instant. All right, that's calculus, kids. I'll stop. All right, so I've got him there. So those are the 3 main trig functions, and then the other ones are actually called reciprocal functions. They are the reciprocal functions. And so sine, the reciprocal of sine, you're gonna love this shit, which means you're not. Sorry, I'm really sorry. The sine goes with cosecant. Let me write the full name. Cosecant of theta. All right, I've given myself no room for this. Cosecant of theta. And that equals h over y. It's just the reciprocal, right? Cosine, now this piece might make sense based on this, which made no sense. Cosine goes with the secant of theta. It sort of sounds like a character from Lord of the Rings. I am the secant of theta. No. Maybe not? Okay. My precious. And the only one that really kind of is like, oh, that's nice. Why didn't they all go like this? Well, there's a really, really good reason that we will get to. Tangent goes with cotangent. Oh, that makes so much sense. What the shit's wrong with you math people? Yeah. So it's just all the, is everybody cool with that? Just all the reciprocal relationships. Okay, I like it. Woo! So let me make a, let me kind of consolidate some of this stuff here. Cosecant theta is h over y. Secant theta is h over x. Cotangent theta is x over y. So I want you to notice something. How is tangent related to cosine and sine? You guys, anyone see a connection between those? Tangent, sine, and cosine. Is there a connection? I'm going to erase those. You ready?
Why, yes, there is.
Why, yes, there is. Can somebody who hasn't taken trig before, see, sorry, George, because you know where I'm going with this. Tangent's y over x. Sine is y over h. Cosine is x over h. So tangent must be no. What do you get?
The
What's
sine
Sine over
divided by the
cosine?
cosine.
yeah?
Or-
What's y divided by h divided by x divided by h? What happens to the over h's?
They cancel.
They cancel. This is something that students I see they don't trust this much. But that's how freaking division works. If there's something on the top that's the same thing in the bottom, they cancel, right? So that means that tangent theta equals sine theta divided by cosine theta. Do you guys see that? Very interesting connection. All right, so let me do this. Let's do some concrete stuff, please, dear God, Jeff. I understand. Here we go. And then I can finally come back and answer Rio's question from earlier. So let me give you a concrete. All right. That was my 12th puberty right there. I'll give you a concrete example. So here's a right triangle. Let me see if anybody out there, you guys should know this. If this is 3 and this is 4, what does this have to be? Do you guys know? Anybody know? 3, 4.
5.
5. I love it. 3, 4, 5 triangle. 3 squared is 9 plus 4 squared is 16. 9 plus 16 is 25, which is 5 squared. Right? Okay. This is called a Pythagorean triplet. It's also called an Euler triplet, if I remember correctly. And how many of them are there? I think there's an infinite number of them. Oh, shit. I'm getting myself in trouble. I'm pretty sure there's I can't. All right. That doesn't matter. None of what I just said matters. So can somebody tell me, if I put theta right there, can somebody please tell me what's the sine of theta? You can do it. Make sure you guys see that's a 4, that's a 5, 3, okay. Which is the y side?
3.
3 is on the y side. Yes, you guys agree with me? Can you guys see a coordinate system here? This is the x, this is the y, right? And it only works if my angle I'm talking about is in the base. So that's the y side, that's the x side, that's obviously the hypotenuse. So now all this shit's easy. What's sine theta then?
3/5.
3/5. Yeah. Right? Sine of theta is defined to be the ratio of the y piece to the hypotenuse. Let that be easy. What about cosine theta?
4/5.
Yeah, the x piece to the hypotenuse. And then tangent theta, you can actually just look here, or you can look there.
3/4.
Yeah, 3/4. And then, I mean, so allow this kind of problem to be stupid easy. Now, of course, hopefully nobody's like about to ask me, do we have to memorize? Oh, hell yeah, you got to memorize this. Holy shit, you got to memorize this. I have, once we get further in chapter 7 and 8 and 9, I have a collection of all the different relationships we're going to learn. And there's a ton of them. That sounds daunting and exciting, hopefully. I tell you exactly which ones I expect you to memorize and exactly which ones you don't have to memorize. Do you understand? I will tell you exactly which ones. And that is something the math department has sort of come to an agreement on, so that when you go to the next level, if you don't have me in the next level, the other person is going to be reasonable with what they expect you to know. Does that make sense? Why we would do that? Okay. All right. I just like to let you know we do talk to each other sometimes. Well, all the time. It's crazy. And then the other ones are going to be just silly. What would go here? What goes with sine? Who remembers? The way I remember this is
The
S
cosecant.
cosecant, yeah, S goes with C. So that's just going to be this guy flipped, right? So these are kind of dumb now, really. Secant is just this thing flipped. And then cotangent is just this thing flipped. All right, there you go. I like it. All right, so let me give you a different triangle, and I want you to do this one. All right, I'll tell you ahead of time. This one's not going to be as easy. So, of course, this is the one I'm going to make you do by yourself. Sorry. So this is 7, and this is 2. I'm sorry. I can't help but laugh evil, a maniacal laugh. Oh, sorry. And this is my angle, theta. So I want you to figure out these trig functions. Erase this right now. Now, I'm going to step in here in a minute just to make sure you're on the right track. But obviously, what do you have to do first?
Find H.
Yeah, I've got to find the side, or else I can't do basically any of these except those two, right? So how do I find this side?
7 squared plus 2 squared equals,
So basically,
equals the square root of my hypotenuse. Yeah.
of the sum of the squares. Is that cool? So if a squared plus b squared is c squared, c is the square root of the sum of the sides. I don't put plus or minus because it's lengths of a triangle. I'm not going to do that, not yet. I keep teasing that. There will be a point where I say the side of a triangle is negative, and you'll all be like, holy shit, Jeff's hitting the sauce. Well, that's true. Just makes me better at math, though. So yeah, you get square root of 53 here, right? I think, yes. Okay. So, who thinks they have the answer to the sine?
2 root 53 over 53.
I love it. That's the right answer. So if you start here, you're not done because you got to rationalize the bottom. That's what sine is. Oh, that's just yummy. Same thing happens with cosine, so it can sort of cut to the chase on cosine, right? It'll be 7 rad 53 over 53 for the same reason. But tangent's going to be nice, right? What do you guys get for tangent?
2/7.
Yeah, it'd just be 2/7. Kick ass. So what's cotangent?
7/2.
2. And what's secant?
Square root of 53/7.
Yes. All right. Kind of want to go to the beginning again because I don't want to look at this thing. So if you look at what this was originally, you can see what cosecant's going to be. Okay. I really. Now listen, trig is going to get difficult. It is. It just is. We're going to get into some identities and different things and what happens if you take the cosine of the sum of two angles and what does that do and all that kind of shit. So it's going to get, I'm not saying that to make you feel like, oh shit, but this has to be easy as shit. It just does. All the basic trig functions are ratios of certain sides of a right triangle. That's it. That's all they are. But at the same time, I don't want you to think all of trigonometry is easy. No, things get complicated, but just like this is really simple. So if you're worried right now, if you're like, no, this is too easy, I must be missing something. No, you're not. This is it. This is all there is to it. Now, let me ask you this. Let me show you how I would handle this. What if they wanted me to figure out the trig functions for this angle? I could do it one of two ways. I could either redraw the triangle so it actually is sitting on this. So then that would be in the base. Do you guys see what I'm saying? That's probably the way I would do it. Or you could just identify this is X and this is Y, but that gets a little bit weird. So it might be a good idea to redraw the triangle. So if I stand it up like that, now alpha is here. Is everybody with me? Boop. So here's 7, 2 is here. Wait, yeah, there's 7. Here's 7, here's 2, and there's square root of 53. So now I can just, it would just be, now notice this. What's cosine of alpha, for example?
The
You know
sine
what-
of theta.
Yeah, it's equal to sine of theta. Cosine of alpha would be 2 over rad 53, which is 2 rad 53 over 53, which is equal to sine of theta, correct? Isn't that weird? Or,
Yeah.
you know, is that really weird? Is that like, holy shit? Or like, it's the same
It
triangle.
kind of makes sense. Yeah.
There's only so many options for this one triangle. So if I talk about the other angle, there will be connections between its stuff, right? Okay. Let me see. And then you can start to see why things are kind of named the way they are. I can't do this without, let's see. So for example, what would this guy's secant be? Secant is h over x. So what would this guy's secant be?
Square root of 53 over 7.
No.
Over 2.
I'm sorry. Yeah, no. Yeah. Square root of 53 over 2. You with me? Because secant is h over x. Okay. Square root of 53 over 2. And what is that equal to? I'm sorry. Yeah, they're out. Theta. So secant of alpha is square root of 53 over 2. I don't know if that's how I messed you up. Sorry. Secant of alpha is square root of 53 over, which is equal to cosecant of theta. Now, do you see why secant, cosecant?
Gotcha. All right.
Hey, sorry. So there's the connection. So there is a connection. There is a reason we call these things co-shit and stuff. All right. All right. So you do have to memorize these ideas. I always just remember sine likes y, cosine likes x. And then tangent is sine over cosine, right? And then these three just flow from these three. I don't even memorize shit to do with these three, to be honest. I just figure out this one and then I can get that one and so forth.
Yeah, because the tangent relationships are more easy
Yeah,
than
these
the
are
other.
the three basic ones. These are the three I memorize, and then these I can make if I know these. No big deal. Okay. But if you want to memorize all of them, go for it. Let me see, how much time do I have left? I have like no time. Damn it. What else did I want to do? I think that, let me think. All right. I do want to do one thing. Watch. Coming back real quick to what we figured out earlier. I've drawn that very small. I'm sorry. You guys can see it. Okay. Remember what we figured out earlier with this guy was this is x over 2. Let me just do this like it is. So let's say this is 1. This would be 1/2. And this would be, did we ever figure this out? No, we never did. All right. So let me do this. I don't know why. Why did I do this? I never did figure this out. And that's my fault. Can somebody tell me what this side would have to be? Remember this, we had, this is x and this is x over 2. So let me just make this 1. So this would be 1 over 2. I'm sorry?
Square root of 3 or something.
Yeah. So let's see. 1 squared would have to equal 1/2 squared plus, we'll call this y. Is everybody with me? So then I get 1 minus 1/4 equals y squared. Is that cool? Well, that's 1/4, subtract it. I get 3/4 is y squared. I get y is the square root of 3 over 2. And again, I choose plus because right now I'm calling it a physical length. So it can't be negative yet. All right. So what does this mean? This means I can be a little more specific about things. What is the cosine of 60 degrees? All right, so here's 6, sorry?
Square root of 3 over 2.
No. What's cosine like? X or Y?
X.
Yeah. So what's the cosine of 60? It's X over H, right? Right.
1/2 over 1.
Yeah. So this is not different from the triangle I just did with theta and shit and stuff. So it's the same idea. Instead of theta, I've got 60 degrees. Who cares? It's a specific angle. Who cares? But what I'm doing now is, now we know for a particular input of cosine, for 60 input of cosine, I get 1/2. And I know I'm dealing with degrees right now, but that's because we're a little more used to degrees. And then I'm going to bring the radians in. But let me just show you, for example, another way to write this is cosine of what? Who remembers 60 degrees is how many radians?
Pi over 3.
Yes, it's 1/3 of 180. So it's 1/3 of pi. So it's pi over 3. So here's another way to write the same thing. And now I can finally tell you, remember how I said the only time the angle can be degrees is if it's inside a trig function? Because no matter what made up shit I use to call this angle, it still means this angle. So if I call it 60 degrees, great. If I call it blah blah, great. It's still 1/2. If I call it pi over 3 radians, great. It's still 1/2, right? So if it's inside the trig function, it doesn't matter what the hell kind of weird ass imaginary bullshit you want to call it with, right? But if it's outside of the trig function, if it's by itself, like in the area formula or in the arc length formula, it better be the freaking physical definition, which is radians. That's all. So if it's out in the wild, radians. If it's inside a trig function, it doesn't matter. Okay, maybe. Okay, now. What would sine of 60 degrees be? Mal, come with me.
Square root of 3 over 2.
Square root of 3 over 2. How blurry am I, Jeff? It's almost time to be done, Jeff, and you're finally going to make it come to focus. All right. Rad 3 over 2. So real quick, last problem, I swear to God. Let's say here's a really classic problem. Let's say I've got a ladder leaning up against the house, right? And it's leaning at a 60-degree angle. And I know I am 6 feet away from the house here. How long is the ladder? That is a question that you could never, ever frickin' answer before we got to this section. But now I can set up a relationship. I know this side, and I'm asked a question about the hypotenuse, this side. Which trig function relates those two?
The cosine.
Cosine. So I'm asking cosine of 60 degrees equals 6 over h. Can I solve that? Yes, I can, because I know what the shit cosine of 60 is. What's cosine of 60?
1/2.
Freaking 1/2. No, not what 60 is in radians. What's the cosine of 60? Or the cosine of pi over 3? They're 1/2. So do you see how that becomes an equation I can solve now? So h is 12. So now I know the ladder is 12 feet, which is why surveyors can do all their freaking work, because if they have distance plus an angle, they can do a shit ton. Do you guys understand? We couldn't do shit before now. And yes, I've said the word shit several times recently, right? We've learned an insane amount of stuff, right? I'll stop saying shit for now. All we need now is more. We need more. Okay, I know 60, but what if the angle was 45 degrees, Jeff? What if the angle was flipping 135 degrees? What if the angle was 11 degrees? Huh, Jeff? All right, so we got to still fill in some stuff, right? And we want to see how much can we do as humans by ourselves on paper versus how much are we going to have to resort to using the calculator for. So we will be talking about extending the amount of stuff we could do by hand. I think that's enough. I think I'm up against my time anyway. So again, the plan for tomorrow, we'll start with a little bit of chapter 7 and then the rest of the class tomorrow devoted to review for the midterm. I've got the practice midterm. I've got the practice midterm solution video up. right? So you can go watch that. Do you have to do any of the practice midterm? No, you can just do homework. That's a really good idea. Just finish up all your homework and then sort of glance at the midterm and go, oh, okay. And then come tomorrow with questions. Okay. All right, guys, let me know if you need to hang out. Otherwise, you are free to go.
I have a question.
Yes.
If we do good on the practice exam, we should do good on the midterm, right?
Yes. It should be, if you do, okay, if you only focus on the things on the practice midterm that were foreign to you and kind of firm that up, you should be fine on the actual midterm. It's not going to be out of left field.
Okay, and did I read or hear correctly that the practice exam is half the questions of the actual midterm?
Yeah, I think I said that specifically. I think the actual, yeah, in fact, I finished making the midterm today, which is kind of early for me. But yeah, I tried to make it, what did it come out to be? It came out to be like 20 questions. And I think the practice midterm is insane. It's pretty long. So I think it's roughly half the length of the practice midterm.
Half?
Yes.
The practice midterm it has 14 questions.
No. That's what an asshole teacher would say, right? I remember we asked how many questions in the quiz, and the guy said 4, and they gave it out, and each one was like A through G.
There's like different. There's like parts A's, B's, all
There
that.
we go. So when I tell you how many problems, I'm counting the A, B, C, D, because those are problems. Yeah, sorry, buddy, I didn't mean to. But I think I counted them up, and they were like, I can't remember.
All good.
But yeah, so it's roughly half the length of the practice midterm. So what exactly did I cut out? Well, we'll all find out on Thursday. I was drunk when I did it, so I couldn't even tell you.
But basically, the concepts of different problems will be the same on the actual midterm.
Yeah, that's exactly the way I would say it. That's a very teacher way to say it.
Okay.
Will the practice midterm be just like the midterm? The concepts that are on the practice midterm will also be on the midterm. So that's perfect. I love it.
All right, I'm gonna go study.
Okay.
All right, have a good night.
You too.
How would I retake the last quiz?
How would you? You just see what I marked wrong on the quiz and then just resubmit it in the same place.
Okay, thank you.
Does that make sense? I mean, you took it in the first place, right?
Yes.
Okay,
yes.
good. So then you just see what you got wrong, redo it on another sheet of paper, and then scan those corrections and turn it right on top of your old quiz.
Okay, thank you. Have a good night.
You too. 6, 7, 8, 9, 10, 11, 12.
Have a good night.
16, 17. You too. 19, 20, 21, 22, 23, 24. 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 40. Holy shit, there were 41. Yeah, so it is basically half as long as the practice midterm.
So I photographed the unit circle like cheat sheet that I made. It's like 1 page long. Can I send it to you to see if it is the way you would teach it?
Yeah.
And also if anybody else wants it.
Do it the other way around. You ready? Let me show you what I'm going to give to you guys when we get a little bit further. If I can move. What's going on with this? Why can't I move? Hold on. All right, there we go.
It did freeze for like a second.
Basics. This is something you guys can't see yet. This looks very much like.
Yeah, but mine's rainbow.
Oh, okay, sure.
Although I don't have the domain and range written on it yet.
But that's for your notes anyway. This is all stuff you guys have to know. You can't use them as notes on a quiz or a test. Yeah.
Mm-hmm.
So I don't care if you have your own. Yeah, sure. Have your own notes. It's beautiful. You can't use it on a quiz or a test though.
Okay.
So once we get these figured out, and of course you can see some of the, you know tricks. So there's your square root of 3 halves and 1 half and all that kind of stuff. We'll finish this out and then I'll just make this official, give this to everybody. It kind of has this stuff about the graphing stuff, but I can reference it later when we get to chapter 8.
I mean, honestly, that I haven't seen the graphing one before, so that's nice.
Yeah, let me show you some real quick. Can you see this?
Yes.
This circle? Yeah, now watch.
Okay.
All right.
Yeah.
Isn't that neat? And I could do that for cosine. You can just kind of watch them be created. It's kind of neat.
I assume you can type in a value for alpha too.
Yes, I can. I can do
Yeah.
all kinds of shit. All right. I got a few
neat.
neat animations. Yeah.
Yeah,
Alright.
I haven't messed with Desmos ever, so.
Oh, it's amazing. It really is amazing how much you could do with it. And to be honest, I stole this from somebody else.
Yeah, you said like a student made it or something?
No. Student made the 3D plotter.
Oh, okay.
Yeah, I'm
That's
talking
right.
about this Desmos kind of program thing. Here.
Hmm.
Not
Yeah.
the Desmos, though, not the whole thing.
Well, Rio, you raised your hand when I jokingly asked the teacher, did you want, I can send you a photo of what I took a picture of if you want to like send me your email or text or something. Maybe.
She can share her notes with you if you want.
Yeah.
Oh, well, that'd be helpful.
If you want, I don't mind. I'm proud of them, so I want to like show people.
Oh, okay.
Well, if you
So-
send it to me and I like it, I can put it up as just another reference, right?
Okay. Yeah,
Yeah.
I can. Do you want it in the what is it?
Canvas.
Canvas messenger? Okay,
Sure.
cool. I'll send it that way.
Okay.
Thank you, though.
Have a good night, you guys.
See you. Everybody else okay? If you're really out there. All right, I'm gonna head out. Bye, people who are definitely there.